Hello! Welcome to today's lesson on the Rutherford model and the Bohr model.
Hi, I'm Ernest Rutherford, a physicist from New Zealand. Today we will explore my alpha scattering experiment. Let's begin.
Welcome, everyone. In today's lesson, we will firstly explore Rutherford's alpha particle scattering experiment. Secondly, we will explore the transition to the nuclear model, proposed after the alpha particle scattering experiment. Finally, we will study Niels Bohr's refinement to the atomic model. So far, we've covered the historical development of the atomic structure. You are familiar with the Dalton model, which represented atoms as indivisible particles with no inner structure, and how the Plum Pudding model depicted the atom as a positively charged sphere with negatively charged electrons embedded within it after J.J. Thomson's discovery. In this lesson, we will build upon this knowledge and look at the next scientific discovery, which is how Rutherford's alpha particle experiment led to the development of the nuclear model. In 1909, Ernest Rutherford and his colleagues conducted a groundbreaking experiment that would challenge existing atomic models and lay the foundation for the modern understanding of atomic structure. They fired alpha particles, which are positively charged, at a very thin sheet of gold foil. Based on the prevailing Plum Pudding model of the atom, they expected the alpha particles to pass through the foil with minimal deflection in a straight line because they thought the positive charge was spread out evenly throughout the atom, like plums in a pudding. But this didn't happen. Instead, while most of the alpha particles were not deflected and did pass straight through, a small fraction were deflected at large angles, and some even bounced straight back. So what do the surprising results of this experiment mean for the structure of the atom? As we have said, based on the Plum Pudding model, they expected the alpha particles to pass through the foil with minimal deflection. However, the fact that most of the alpha particles pass through without significant deflection indicated that the atom is not a solid mass, but is instead composed largely of empty space. If the atom was solid, we would expect more of the alpha particles to collide with the gold atoms and be deflected. The lack of significant deflection for the majority of the alpha particles suggests that they encountered no substantial obstacles as they traveled through the gold foil. This observation directly challenges earlier models of the atom, such as the Plum Pudding model, which suggested that positive charge was spread out evenly throughout the atom. Instead, Rutherford proposed that the atom consists of a small, dense, positively charged nucleus at its center, with electrons orbiting this nucleus. This nucleus occupies only a tiny fraction of the atom's volume, while the rest of the atom is empty space where electrons move. Let's break down the observations from the experiments to understand what conclusions we can draw from them. Our first observation is that most of the alpha particles pass straight through the gold foil, meaning that the atom must be empty space. Secondly, some of the alpha particles were deflected by a small angle. This means that the mass of the atom must be concentrated in an extremely small volume in the center. Finally, a very small number of alpha particles came back in the direction of the detector, deflected more than 90 degrees. The resulting conclusion is that the center of an atom must have a strong positive charge. Also, the electrons must not be in the center of the atom. They must be orbiting the nucleus. The findings from Rutherford's experiment led to the development of a new atomic model, moving away from the Plum Pudding model. As we have discussed in previous lessons, the newly proposed nuclear model depicted the atom as having a tiny, dense, positively charged nucleus at its core, which contains most of the atom's mass. Around this nucleus, negatively charged electrons exist and move around, but the exact nature of their movement wasn't yet fully understood. Though the nuclear model was a significant leap forward, it still had inconsistencies. In 1913, Niels Bohr refined this model further by incorporating the concept of quantized electron orbits. Recall from our lesson on electronic structure that electrons orbit the nucleus in shells that get increasingly further from the nucleus. For example, sodium has 11 electrons. What Bohr's refinement of the model tells us is where those electrons lie. Using our electron configuration rules, we know that sodium has 2 electrons in the first shell 8 in the second shell and 1 in the third shell. The idea of shells is precisely what the Bohr model added. Prior to this refinement, it was not known how electrons behaved around the nucleus, or where exactly they were. Bohr suggested that electrons orbit the nucleus at specific distances called energy levels, similar to planets orbiting the Sun. Much like planets, electrons cannot go in between orbits. They can only exist at their particular energy levels. In today's lesson, we delved into the evolution of atomic models, tracing the development from the Plum Pudding model to Niels Bohr's atomic model. We began by recapping J.J. Thomson's Plum Pudding model, which was soon challenged by the results of the alpha particle scattering experiment conducted by Ernest Rutherford. We explored how Rutherford's experiment led to the nuclear model of the atom, which proposed that atoms consist of a dense, positively charged nucleus surrounded by electrons in mostly empty space. We then moved on to Niels Bohr's refinement of the atomic model. Bohr suggested that electrons orbit the nucleus in fixed energy levels or shells, and that they can move between these levels by absorbing or emitting specific amounts of energy. This model helped to explain the stability of atoms and the emission spectra of elements. That's all for today. See you next time.